All right, AP Calculus. We are here today to learn about the fundamental theorem of calculus, or the FTC. Now, whenever someone tells you something is a fundamental theorem, hopefully that tells you that it's something that's pretty important, and certainly this is indeed pretty important, almost certainly the most important thing we'll learn this year. The fundamental theorem of calculus does two things. It connects to the big topics we've been working on all year, and then it connects derivatives and antiderivatives. And it also connects them to definite integrals, which are what we think of when we first talked about definite integrals. We talked about that as an area under some curve. Okay, and the next thing that it does is it shows that integrals and derivatives are truly opposites, as you probably suspected already. Okay, so that's what's going on with the fundamental theorem on the big picture. Let's get to the nitty-gritty. There are two parts today, and we'll start with part one. Okay, part one says this. If your function f of x is continuous, and integral of little f of x dx equals big F of x. So basically just saying big F of x is any antiderivative. So you integrate little f, you get big F again like normal. Then if you take the definite integral from a to b of f of x dx, this gives you the antiderivative evaluated at the top bound minus the antiderivative evaluated at the bottom of the bound. Now, you might just say, hey, this is really easy. We learned about this in honors pre-calc because it's like talking about, I don't know, definite integrals. But I want you to think about what this means. This is relating the area under some curve to doing the opposite of a derivative. So it's saying to find the area under some curve, no matter what it is, you just need to find some random antiderivative and plug in 2 points that. And that was a revolutionary statement, and it's hard for me to underestimate like how important this is and how crazy it seems. No matter what your curve is, to find the area under it, all you have to do is take the antiderivative and plug in 2 points. Great. And this turns out to just be like extremely useful, because if I want you to find, say, the integral from 1 to 2 of x squared dx, well, graphically, what that's saying is if you have the the function x squared, and you're trying to find the area from 1 to 2. Now, you could estimate that shape, but what if you wanted to find the exact area of that shape? Well, all this is saying is you just have to take the antiderivative of this and get x cubed over 3, and then evaluate it from 1 to 2. So this little bar, when you put it after an integral, it just means evaluate at 2 and at 1, and then subtract. So that's saying, okay, the antiderivative of x squared is x cubed over 3. Now when I plug in the 2, I just get 2 cubed over 3 minus 1 cubed over 3, and this turns out to be 7/3. So that's remarkable that we can find this area under a curve by just taking an antiderivative and plugging in 2 points. Truly beautiful, truly beautiful. So this is the strategy we're going to use to evaluate any definite integral till the end of the year. We just find an antiderivative, and then we plug in. So let me show one more example of that. So if I ask you to take, I don't know, the antiderivative of, the integral from pi to 2 pi of 1 over x plus cosine x. Again, this is a weird, wacky function that finding the area of it would be somewhat difficult. But this is one that you can find. It actually cleans up really nicely. You can turn this into, all right, so you integrate 1 over x. That's ln of absolute value x. Derivative of sine is cosine, so this side's still positive, going from pi to 2 pi. So one thing I'll do when I have two things added like this is I'll plug in the first one in parentheses, so that's ln of 2 pi, I can drop the absolute value there because it's positive, plus the sine of 2 pi, and then minus in parentheses, and then I'll plug in the bottom bound, so I'll plug in ln of pi plus the sine of pi. And I'm subtracting that whole thing. Okay, so this is ln of 2 pi. The sine of 2 pi is just 0. The sine of pi is 0 too. That actually worked out really nicely. Minus the ln of pi. So you could simplify that to be the ln of 2 pi divided by pi, also known as the ln of 2. If you just left it here, that's fine too. So that's, again, this is the area under that wacky curve. So all we have to do to find that area is just to go ahead take the antiderivative, plug in the top, plug in the bottom. Okay, this is such a big fundamental idea that I want us to really focus on this for this video. Let me just show you one more, and maybe you can pause this and try and work it out on your own, right? What if we try and integrate 4x plus 7 going from -1 to 2? All right, you can pause and work that out. All right, so we'll get 2x squared plus 7x going from -1 to 2. When I plug in a 2, I get 2 times 4 plus 7 times 2. And then I'll subtract, then the whole thing, I'll plug in the -1, so 2 times 1, and then minus 7. So let's see, I will get 8 plus 14 minus a minus 5, so that turns out to be 27. Okay, so those are definite integrals. We can calculate them with an antiderivative and plug in the points. That's what I wanted to go over in this video, just a huge idea. Okay, thanks for watching, and I'll see you in class.